Hey everybody, welcome to PCB Routing on Saturday. I'm Odin. I have about 25 years of experience in making PCBs, and here's where I share my knowledge and screw ups and whatnot. Today we're going to be making a Power of Ethernet device as an Ethernet device, which also gets power over the Ethernet lines. If you're new, you can see us making the source side, the switch side in previous episodes. Um, the device that we're going to be making today is going to be a power signature analysis device. So basically, we measure voltage and current on three-phase mains power cables, mainly to electric motors. You can also do diagnostics on other stuff, but electric motors is the typical use case. And by measuring very precisely at relatively high frequencies, not high frequency, but seeing as most measurements are something like 20 hertz, you look at something like 100 kilohertz or something measurements of power signature, then you can see actually a lot about how a motor works, whether it's going to break in the future. You can see the inner temperature of the motor based on the change in reluctance of the uh, uh, motor itself. That changes with temperature, so you can see that. You can see problems with gears. You can see winding shorts over time. You can see broken winding is actually not that hard, but yeah. So we have some power signature analysis devices in rail infrastructure and nuclear valve, maintenance stuff, and a bunch of other electric motor stuff, oil and gas pumps and whatnot. If it's expensive, if it breaks, then you probably want to know when it's going to break. And if you do power signature analysis, then you know when it's going to break. And so that's what this thing's used for. From the nerd side of things, it's Power Ethernet PD device. It's running off of 100 megabit internet Ethernet with the WISNet W5500 chip. Actually, we could pull up the schematic as I'm describing it from a nerd perspective. And we come in here, we have our uh, Ethernet connector. It's not the waterproof one this time. It's a standard Ethernet connector, and it's a mag jack, which means it's got the magnetics in the actual connector. Um, that's good from an EMI standpoint. It's also just easier. Like, you don't have to put down as many components. You don't have to worry about as many diff pairs and whatnot. And out of this mag jack, it's a PoE capable mag jack. You definitely want to use one of those if you're doing PoE stuff, because the non-PoE mag jacks may have connections from center taps to each other or to other stuff. And you definitely don't want that if you want to be running voltage over the center taps, right? So the center taps, all four of them are broken out here from the magnetics. I did a little more of a deep dive on how PoE works on the industrial switch video. So I'm not going to go as deep in here, but check that one out if you don't understand what center taps are or whatever. Um, so center taps go into a rectifier, which basically we don't know which cable pair is which, like what's the plus side, what's the minus side. And even if we did, some uh, uh, highly capable engineer like myself might use the wrong cable, like a crossover cable or something. So even if you did have like a specific center tap order that this one's high and this one's low and whatever, then you could still short it out, which would be stupid. So basically it's undefined which center taps are high and low, and so you just have to run it through a rectifier. Rectifier, we're not going to be pulling a whole lot of current, so it's just you know, 4 2-diode things. It's the cheapest rectifier if you're not pulling a bunch of current. It's also a little bit smaller than the big ones, because the big ones are the bridge rectifiers are usually aimed at like mains power and whatnot. So if you're using that in this case, then you don't need the big spark gap distances and whatnot. So I just if I'm not pulling a bunch of power, I just use the double diode in an SOT package, and then 4 of them. I mean, they're dirt cheap. So that's going to turn into plus and minus, and we're going to go through flyback transformer. Now, the reason why we're going through flyback transformer is because flybacks are isolated. So as per the Power over Ethernet specification, you have to be isolated on the device side, and you can be optionally isolated on the source side. Now, there is a bit of an as-if rule, right? So if you're doing like a temperature sensor or something, well, your ground isn't touching anyone else's ground, so whether you're isolated or not doesn't matter. So in that case, you can be using something like a buck or whatever on the device side. But in this case, we are connecting to Hall effect sensors, which are connected to mains power lines, right? So we are connected to something else. And so we better not be also connected to the switch with our ground, or something's going to burn, right? So that's why we're using the flyback transformer, because it's isolating. Like we go in here, you got, the control side is making magnetic fields in the transformer, and then the output side is completely galvanically isolated. I mean, we do have a high frequency filter here, but this is 2 kilovolts, so as long as the two aren't more than 2 kilovolts apart, then nothing's going to fry. I think the transformer is also something like 2 kilohertz. Kilovolts. So yeah, that's where we're using that, and I think I found a first error here. If this is 5 volts and I've got a connected 3.3 volt line, I think we actually need an LDO in between here. So that's a good thing I'm explaining it, because I screwed up in the schematic. That's what prototypes are for, right? I delete that just to make sure that I don't forget to fix it later. So going the other way through the mag jack, from the mag jack, we've got the data lines of the Ethernet, and they are going into the 2 diff pairs, because we're only doing 100 mbit. We're not doing the full gigabit, right? So we only have 2 diff pairs coming out. That's going into the W5500. It's a pretty cool chip, actually. It's a Mac and a PHY. So you can talk to the Mac through SPI, and it's got the 100 megabit PHY on there as well. So you can use like Raspberry Pi Pico plus this is full solution. WisNet actually has a RP2040 together with the W55. I think it's called like the W55 RP2 or something like that. That's probably not exactly what it's called, but it's something like that. It's like a combination of the 2 part numbers. And if I were to start again today, I would definitely use that chip. I'm using this combination because I already have like working firmware and a bunch of other boards that use it in that combination, and I've got a bunch of them, in my personal stock at JLC and whatnot, because we started working with this combination of chips before WisNet came out with basically the combination of chips that we're using. Somewhat a vindication of chip selection, right? If the manufactured pair is the same. I think they actually use slightly different SPI lines, which are wire bonded between the 2 chips within the same package than I'm using. But that would be a relatively trivial firmware change. I just don't have the time to test it all and whatnot. Now here we have the RP2040. It's the microcontroller for Raspberry Pi. It's the first one. There's now the second one is out, which is got better protection. It's also got better bootloader support. It's also, got better low power modes. Yeah, it's a buffer kernel with better synchronization stuff. And yeah, it's also slightly more expensive. For this kind of application, it doesn't actually bring a whole lot of advantages because we don't care about low power, and we've got enough processor. Bootloader would actually be interesting, but we already kind of hacked that, so it's not really a problem for our design. But again, I'm not quite sure why WizNet didn't go with the newer Raspberry Pi and the in their hybrid chip package. But yeah, it's fine. Bootloader's a little harder because you can't like map flash back and forth, but that's getting into the weeds in software stuff, or firmware stuff. Then we have a Mac chip, which I mean, the only real reason why you buy this chip, all it does, it just has a number in it, right? But it's a guaranteed unique MAC address, and so you don't have to worry about, if you're production programming a whole bunch of these things, you don't have to worry about making sure to give every device its own MAC and buying a block of MACs and all that kind of stuff. You buy this 20-cent chip or something, plunk it down, and read out what your MAC number is, and you have a unique MAC number, right? Yeah, it could be theoretically more efficient in a perfect world, but production programming is not completely solved problem. Although Seger stuff's actually pretty good for production programming. I'm still plugging them, even though they no longer sponsoring our conference, I think. So I'm honest. Yeah, no, they're pretty good stuff, but it's still not a completely solved problem. So yeah, it's that's why we have that chip. And then here's the programming for the programming pins for the microcontroller. Then here we're getting into the sort of more interesting part, or at least the more sort of unique to this design part. We have a 8-channel diff amp. I don't actually need a diff amp in this case. I'm just using it because I already have firmware drivers written for this chip. If I were to do it all again, I would probably do a single-ended one. However, I do actually have an advantage of seeing things go negative, right? And also, one of the big advantages of this this chip, let me show you guys the part number, is that it does like a parallel sample and hold, and so it's 8 channels. It only actually has one ADC, but it has like 8 capacitors and latches that'll fill them all at the same time, if you will, right? And so if you're doing power signature analysis, that's actually interesting because you don't want to be seeing like some weird spike on one line and not on the other lines, because your sampling went 1, 2, 3 rather than 1, 2, 3 all at the same time, and then sampled them in series. Yeah, and so the whole reason I'm doing this here is, it's basically a poor man's voltage reference, right? I use this LMV601 all over the place, so I got a bunch of those in stock. And I could also just use a real voltage reference here, but I don't actually care what voltage it is. I just want it to be somewhere in the middle between plus and minus, right? Because I also want to be able to do the, scratch that. I was thinking programmable gain array, but this thing doesn't have a programmable gain array. I was thinking of another ADC. But in that case, it is important to keep the 2 rails like close to each other in the middle. Yeah. Okay. So that's our analog sampling part here. And then what we got here is our mains current and voltage running through these three lines. Here we have, for our voltage sampling, it's basically just a voltage divider to a common center thing, right? For one, we want to establish some common center of the voltage of all three, right? Which should theoretically be relatively stable in a working circuit. I mean, a lot of buildings are wired such that the center is actually connected to Earth, right? So we have common, and that's going to be, you know, the center between all three of the lines, and we have a capacitive and resistive divider, right? It's a little counterintuitive. You need well, I guess, yeah, you need the big resistor and the big capacitor on one hand, and then the small capacitor and the small resistor on the other hand. That way you have, in the center, you have, you know, a voltage divider that's not just resistive. Actually, no, this is the wrong way around, right? We're finding my errors live. I think this is the wrong way around, because you won't, the smaller capacitance is going to be having the bigger voltage gap across it. These should be the other way around, but I'm not going to switch them around right now. I'm going to think about that more later. But again, I probably found another bug in the design. Well, I'll explain to you. It's kind of the rubber duck situation. You can tell this is new. We've mostly been doing voltage contactless so far. And that's proprietary enough that I don't want to open source it and tell everybody exactly how it works because we're kind of the best. Well, I don't know if we're the best, but we're definitely the best at that price in doing that. Yeah, that's how we've been measuring voltage so far, because then we're like completely contactless and no, you know, we can kind of guarantee pretty easily that there's no feedback coming through to our device. In this case, you know, we have common. Common is basically our ground. And so since we're isolated on the flyback, you know, the ground of the whole system is essentially the common rail between these. And so, yeah, there's not going to be, you know, ground loops and whatever possible because we're isolated flyback. But that's harder to explain to people who are doing safety checks. So yeah, so that's why we've been doing it differently so far. But there are a lot of applications where it's not that critical, like if it's not a nuclear plant and you want to be cheaper. This will certainly be cheaper and more precise. And so that's why we're doing this. Yeah, if you're in some critical infrastructure application, or, you know, I guess define critical, you know, if you're in some infrastructure application where it's just expensive if things break, then, but, you know, nobody dies, then you can certainly go with this design. And for the current side, we have Hall effect chips. I named my second son after Edwin Hall. He's a pretty cool dude. Discovered the Hall effect. And I guess I'm not going to get into exactly how the Hall effect works. Basically, you have two kinds of Hall effect chips. You have one where you're not connected to the wire. You kind of have the wire running under the chip at like a known distance away from the chip, and you measure because what Hall effect measures is the magnetic field, right? And from the magnetic field, you can deduce current. Now this chip is a lot easier to work with because you have current flowing through the chip from, one set of pins to the other set of pins. What that looks like inside the chip is they, go to a place within, in the middle of the chip where you got shielding on the bottom, top and bottom, and then there's one little little bend where the Hall effect is measured. So you measure the magnetic field strength at a very known location, known distance, a bit of shielding around, so you're more precise and you don't have to calibrate it or anything. It comes like pre-calibrated and whatnot. And so the whole point is that the left side's not connected to the right side, right? The left side's connected to the Hall sensor. The right side's connected to basically just a wire that goes through the chip in a very defined way. Or with a very defined geometry is probably a better way to put it. So yeah, so that's the whole circuit. That's what we're going to be routing today, and I think we're going to. I got stuff somewhat sorted. Like this. This is going into like a little rail mount enclosure. I'll drop the link in the as a comment below this after I don't have it ready to go. So otherwise, I'd show you guys what the case is. It's like this dirt cheap, like $2 or $3 in small amounts rail mount case, which kind of snaps together in sort of cheap plastic. And yeah, it's got a hole at the bottom, which is exactly the right size for one Ethernet connector and one of these connector plugs, like the big, typically green ones. I'm blanking on what they're called. But anyway, so here we have mains going up and down here, and then here we have the Ethernet. Now, some of the things that we want to think about with this design, which we haven't gone through in previous episodes, is, for one, we're going to have some pretty serious current flowing through here, right? And so we're going to have to worry about making tracks big enough. Guess a general rule of thumb is like most boards are, I think, 1 ounce copper, which is what, 35 micrometers or something. Europeans use different units than 1 ounce, because it's like 1 ounce per square foot or something. That's probably wrong. 1 ounce per square some unit of area. And that turns into copper thickness. That's like, Europeans make fun of Americans for their units, and that's another one of them. It's kind of easy to make fun of. But anyway, so yeah, so if we're 1 ounce copper is standard. Outer layer and the inner layers, I think, are like a ½ ounce is standard. And if you want anything else, then it's going to be more expensive. In this case, we probably want to bite the bullet and make it thicker than that, because we don't want the traces being 20 degrees C higher than the rest of the world or anything. We don't want to be creating a bunch of heat that we got to get rid of and all that. So doubling the thickness of the copper is going to make the trace widths that we need go down, right? And also, if we do 4-layer board, top layer, 2 inner layers, bottom layer, all of them 2 ounce copper, then we can use all 4 going through here, right? Because there's going to be not much else going on. And yeah, I mean, if you want to know like how much a copper track is going to heat up based on its width and what copper board and whether it's an inner layer or an outer layer and all of that stuff, that used to be like you'd have to know the formula and all that kind of stuff. And at this point, just ask AI. Like at least Grok is always right, as my experience at least. So yeah, just ask Grok and it'll tell you. So yeah, I think we're gonna do something like two. Oops, it's a line tool. Something like two. Yeah, that's about right. And then we're gonna do them on all four layers, uh, which is actually not all that easy to do with KiCad. Like it kind of tries to be smart and say, oh, well, you already got that connection on the top layer. And so, yeah, if you connect it to like staggered different vias, then it'll work. But the other thing we have to worry about with mains power is the spark gap distance, as in how far do we expect a spark to be able to go, is, there's a bunch of different standards for this, and it also depends on like barometric pressure and I think humidity and like a bunch of other stuff. So it's going to be different if you're, in airlines or, things that go high for some reason. And it's also one thing you're going to have to worry about is how dirty your environment is, because spark gap through air is, according to the standards, something like 3 millimeters for European mains. So normally 220 volts AC, something like 350 volts is like the max that you can actually see. And so that spark gap distance is 3 millimeters. And go figure, this connector that's used for mains is exactly 3 millimeters. But if you're in a dirty environment, then the dust might actually conduct better than the air, in which case your spark gaps are going to have to go up, right? So that's one thing to think about. Now, the spark gap distance through air is actually a lot, air is actually a lot more conductive than PCB insulating material. Go figure, right? You can do better than air. uh, so if you are using, if you've got your traces going through your board with solder resist on top and all that, right? Then I think something like uh, 8 millimeters or so is going to be more like the gap. I mean, talk to an AI about this before using my advice in your own design. Basically, the reason I'm mentioning this is so that there's something you watch out for, right? Um, so I'm going to use um, a gap of 8 millimeters between the traces when they're not connected to the outside world, and then or sorry, not connectable through air, as in when they're next to each other on the board, and 3 between possible air connections, right? So that's one thing we're going to have to worry about. And the second thing we're going to have to worry about is these Hall effect chips. They are shielded where they're actually measuring the Hall, but if we say, okay, oops, this is going to be, let me just use something smaller to kind of show you where this is. Oh, no, this is one way around. Oh, okay, I get it. Okay, so we got something like this, just for the sake of argument. These are thinner traces, but I'm just demonstrating. Oh, wait. That is the wrong way around for some reason. Should I be swapping these just so that that'll work? Yeah, I probably should. Anyway, to finish the first thought before I get to the second thought, if I'm going, from here to here and then from here to up there, if I just run that trace right through here like this, then, well, I have a different mains line going right under the spot where I'm measuring the Hall effect, right? So that's another gotcha with Hall effect. So we're going to need to go around. And then the second gotcha is or the second thing I was thinking about was how the chips are the wrong way around. So I can just change these around, and then it's going to work, because it doesn't really matter which one's up top and which one's down below. That was like the magical position. And then here it's going to be, what was the distance? Yeah, something like that. And then there it's pin 1, pin is a little bit. I mean, this probably doesn't really matter that much that I get this exact. It just needs to fit in the case. If it doesn't, then I can fix it. I'm definitely going to screw up something else on the board anyway. And so I have one iteration of buy the prototype and then check. Okay. So now, yeah, now we've got going up to this part, and then from this part going on to the next one. That's all working out. Okay. So the other thing that we have to worry about when we're close to mains, which a lot of people overlook and can take a while before it bites you. Now, those are obviously the worst kinds of errors. Mains, if there's AC flowing through it, then you've got some number of volts per millisecond, which is the highest, right? Let me get paint out here and kind of draw what I'm thinking about here. So we've got, here's the zero line. That's a terrible zero line. Here's, wow, I really can't draw with this mouse, but I don't want to get my pen out and all that. Okay, so there we've got zero line, then we got the mains going up like this and some kind of a sine wave, right? Well, right about here is like the sharpest, the sharpest voltage change that you're going to see. But considering, that you've got like this, peak to peak is going to be 20 milliseconds in Europe, and what, 16 point whatever, whenever 60 hertz, no, it's more than 16 point. It doesn't, I don't care. Something else in America, something slightly smaller because of 60 hertz rather than 50 hertz. So that's actually super slow. And so, your rate of change, like your capacitive coupling of your stuff to the mains is going to be, it's not going to be a huge problem because it's not a super fast rate of change, even though it is a high voltage, right? But if somebody's switching relays somewhere, like you don't really know if you're going to be part of that, but especially, if somebody's switching motors on and off, then they're probably doing it with a relay. And there's a smart way to do that, where if you get like the switching signal here, say, then you're going to have some smart circuit that's going to wait until it gets to the next zero crossing, and then it's going to switch here, right? So that's a smart way to do it. And if you're doing, hobby electronic stuff, then, put some comparator on there and do it that way. Like, do yourself a favor. But critical infrastructure is often older than me. And even if it is new, then the technology is often older than me. And so that used to be expensive to do, to wait till the next zero crossing and switch it, clean, right? So what if somebody switches it on like here, right? Like closes the relay right at that spot where the first spark of the, relay's read thing to the connector goes there, then you could have, your whole hundreds of volts within, microseconds, nanoseconds, right? So that's a really, really, really sharp edge, right? And so the thing that, I think I left this wrong just to show you guys, the thing that we could have here as a problem from that, for example, is we've got, where's our reset? Here's run. Oh no, I fixed it. So sometimes you'll see pull-ups on things like reset just as a resistor. And if nobody's doing weird stuff, that will probably work. But without this capacitor, then you have a capacitive coupling of this stuff two mains thing, which is going to be, tiny capacitance, right? Because they're going to be probably far away from each other. But then you also, but that, on the other side of that equation, like the local capacitance, it's just going to be the pin capacitance of, that pin and the wire bonding to the chip, and that's about it, right? Gate capacitance of whatever's sampling, right? So you got tiny capacitance versus tiny capacitance, and if the one side is switching at like 100 volts per nanosecond, or more than that, then and not just fast but also far, then you could flip the reset, right? Uh, Even if this capacitor is just far away, you could still potentially flip the reset if the mains is somewhat close, right? There's, don't underestimate this. Like, this has bitten me twice. Even though I knew about it, I thought, oh well, it's far enough away, it'll be fine, and then bit me again. So yeah, do worry about that kind of stuff. I mean, it's probably only going to happen like once, so you don't really have to worry about like Ethernet stuff. Maybe you'll have one packet blown. You're using TCP anyway. It'll resend it. It'll be fine, right? But things like reset can really ruin your day. Yeah, so that's another thing to think about if you're close to mains. So now, after I've explained all of this, then maybe we should start routing after almost 40 minutes of explaining stuff. Um, so let's see, we got another cool part of KiCad is you can select like whole hierarchical sheets, and then it'll select all the components on that, right? So this, we're going MagJack into this. We're starting with the MagJack, right? And so that's this. That's the controller. That's the McAfee and whatnot. We also have the rectifier for the power of Ethernet stuff, which is going to be these guys, right? The question is, which one of those should go next to the connector or closer to the connector? Now, on the one hand, you could argue, well, these are switching super high frequency. These are not. Maybe we should, minimize high frequency lines going around the place, and that's a valid argument. On the other hand, the center taps are potentially a source of, surge and burst and whatnot. Like, I guess I should draw this just to come. Oops. That's the one I want. I get rid of all this. So the way power of Ethernet works is we have, or the way Ethernet works is we have a split core here and a split core here, and this comes from the outside world, right? And this goes to our chip, right? We also have a center tap. And if you're not in a power of Ethernet setting, you're just going to do center tap to ground, and that reduces noise, right? That's the whole reason for center taps. But in the PoE example, we're going to be getting our power through this center tap, right? So this is one of the PoE rails. And so that center tap is not our local center tap that's connected to our chip and stuff. That's the other side of the magnetic core's center tap, right? That's the one that goes, that's hardwired to stuff that goes outside, right? And so if you're thinking about like surge and burst test EMC stuff, then for these lines that are going to the controller, well, they're on this side, and there's this whole big old air gap here, right? So you don't have to worry about that. I mean, there's no way that there's going to be more energy coming through there than a saturated core will give you, right? At some point, it's full, and that's the amount of energy you're getting, right? And so from a EMC standpoint, this one is going to be more interesting. And so what we want to do is keep those short, right? So I think I'm going to do something like just go across here, and then maybe we'll do the other ones going on the underside of the board. I'm trying to keep the right order such that why isn't this lining up? Such that I don't have to route past each other there, because the other side is all just plus minus. So I guess I want that one first. I guess it doesn't really matter. It just depends on which way around that pin I go. Let's just do this. Okay, so we're doing those first. Yeah, I guess we also have like the isolation through the flyback. So maybe I can actually even do flyback next, and then just scooch the other, the ones, these lines, scooch them like on the underside of the board over to here, because we kind of are in sort of two different domains. So you've got the domain that's connected, like hardwired to the outside world, which is half of the flyback and the rectifier. And then we have the our side of the magnetics, which is isolated from the outside world. And we'll do that up here, because then we'll just have that area down here. And if something starts toggling up and down or anything, then we're far away. But I think I probably have to figure out how far these chips go away from here, because otherwise I don't know how wide I can be. This is definitely going to be a tight board, me fitting everything into this half of the board. So why don't I start routing those guys first? Now the question is whether I want to actually go through the whole different constraints for these nets kind of a thing, or whether I'm just going to try and be careful. Because the thing is, I am going to need the 8 millimeters, or 0.8 millimeters, sorry, between the tracks here, like this. I haven't measured that yet, but will. But between like that track and then this track, oops, like that, well, I don't really care here. It's just, it's whatever the minimum requirements for that copper is, just so they're not actually touching, because they're going to be the same voltage, right? Because they're connected within the chip already. And so I think if I do it with the special net rules, then it's gonna gripe at me because of that. So I think I'm just gonna try and be careful, like famous last words, obviously. Okay, so I probably should start up top actually, because on the other side I'm gonna be going along the back and around the other chips, so I don't mess with their magnetic fields. This side is going to go back here, and this is going to go back here. Okay, so I do want to go. Let's see what. Was it 0.8, or am I misremembering? Oops, something like that off screen. I had it written down, but my Chrome crashed. One second here, sorry. Oh, okay, sorry. So I'm stupid with 8. Oh, I already am doing 0.2 with the board. So theoretically 0.2 is even enough under the solder mask. But I think I'm going to do 3. I'm going to do 3 just to be sure. So something like that, right? So the grid is 0.05. Make it 0.1 so I can just count. There we go. Something like that. And then down to like here, and then I could drop the chip right on top of it. Something like that. Because then this side, I'm going to have to go around the back to make sure I'm not messing with the magnetic fields in there. There we go. And then this guy, I guess I could do a little jog here. It's probably not going to, oops, I'm stupid. I shouldn't be doing that at that distance. Just playing it safe here. So yeah, that's about right. And then I'll be seeing 3 dots here. And then, yeah, around the back of that guy as well. And then to the front, and then within the 3 dots of the grid. And then up and over. Oops, no, that's the other one. Okay, plunk the chip down, something like that. Then I'm just going to via into it from each pin. Because I have to manually move the vias. I haven't figured out this snapping in the new keycad. Like, it somehow seems like I'm fighting it more than it's actually helping me. That's probably just because I'm not used to it yet, and I'm a grumpy old man, and I don't like change. But yeah, I'm gonna figure that snappingness out at some point and not look so capable doing it. Otherwise, you can just, copy paste them. Oops, that's my OCD's not liking that. There we go. Same height as that one. And something like that. That. Oops. Oh, well, there's kind of no good option there. Oh well, without making the grid smaller. But it's fine. That's going to actually totally become my tagline. It's fine. Okay, so something like that is what we're going to do with those chips. And so by doing that, we've kind of established how wide this is. And I kind of also like this because if I do rectifier and then flyback and then Ethernet, and then all the way up here with my Raspberry 2040, then the RP 2040 is going to be in this magical place that's farthest away from the mains lines as well, because that's where we really don't want to screw stuff up with transients and whatnot, right? So I think I'm going to put this dude way up there, something like that. And then, see, let me grab the flyback. Oh, yeah, definitely also need to leave room for an LDO. I forgot. Stupid me. Okay. So let's figure out the geometry of this thing. So where do we have the switching part for this guy? Power PoE plus. There's the switchy. That one's the switchy. So I got it the wrong way around. Okay, so here's switchy, and this is, oh yeah, that's like feedback detect stuff, and that's just connected to ground so that we have a reference. That's not like there's going to be a lot of power flowing through there. So it's basically PoE. Oh crap, this is kind of all backwards. How am I going to be doing this right? Because that is power is kind of going to make my loop big. Oh, I guess that is also, no. Okay, that's ground, yeah. So, I mean, I guess it doesn't really matter where the power is on the chip. We just need a good connection between this bugger and ground. Yeah. So, yeah, let me build this like outside and then I'll move it in. Okay, so yeah, we definitely want this switch side. So is there any reason why we don't connect this, move this like really close to that one? Let me look at the schematic. Okay. Now, yeah, this is why I sometimes don't like it when the footprints are not like built up by where the pins actually are. They're built up by, okay, here's a switchy. So I've got this snubber, which basically swallows the energy when the switches off and the inductor just flies, right? So, you know, if there's any energy flowing, you know, if there's still magnetic flux in this thing, we'll put it that way. If there's still magnetic flux in this thing, pin 4 is connected, you know, to some firm power, you know, some firm voltage, right? And 3 isn't connected to anything anymore because the switch switched off. Well, that magnetic flux is going to be turned into some current, and current with you know, no source of electrons here or place to sink them, depending on which direction the current's going to go. That means the voltage is going to go really high, up or down, if it's not connecting anything. So that's the reason why we have this circuit, right? It's going to dump that into this 10 nano capacitor and then bleed it off over this 10K resistor, right? So that's what that's for. And so that probably should go close to the switch. Okay, yeah, so that's going to plus, because we want to make like the switch line kind of as small as possible. And I keep telling everybody to always name your nets, and then I don't do it. Well, that's stupid. So we're going to do LSW just so we can see it on the schematic. Clear case of do as I say, not as I do. Okay, so now it's called SW, and so everybody knows what the hell is going on. Okay, so we're going to the capacitor. That's going to be, why don't we just grab this guy and then we know what's what. Okay, so this one and this one. And then after that, it's going to PoE plus. So I guess the question is, what is more important to me, snubber closer or capacitors closer? Current noise versus voltage noise. I think at the switching frequency this is going to be at, I don't really care either way. Yeah, so if we're building this up, let's move this away. Let's go. Something like this. And then this dude like scooch right up to there. I guess I could go. I have big components over here. I just have ground and ground. Well, that's going to give me a lot of room to put a bunch of capacitors up. So how big are these capacitors? Okay, here's the big beefy capacitor. That's probably 1210, right? Yeah, I might actually use the 47 micro that I was using on the last stream, because they're 100 volt rated, and I'm already using them in a bunch of other places. And that way I could theoretically get away with less of these. And since I'm space constrained, I think I'm going to do that actually. So how many of these do I have? Oh, I've got 4 of these. So why don't I just throw out 2 of them, make the other, make sure that still connects, make the others 4.7. As I was saying on the other stream, doubling the capacitance, same footprint, might actually not double it at the derating of 48 volts, right? But I'm going to note that, and I'm going to look at it later. Got feedback from last time that I spent too much time in the weeds selecting components and whatnot. Y'all want to see routing. And then I want to make sure, and okay, yeah, there's an LCSC number anyway, so that's fine. I'm going to be selecting that later anyway. So we can just update, and then we only have 2 of them because they're twice the size. Okay, so that is looking good. What is this? Oh, that's, yeah, I'm definitely going to swap that out for ceramic. Because that's too big. I mean, we're definitely space constrained here. I'm not usually the space constrained. So that looks pretty good for like the power critical geometry stuff. What else do we have that I haven't plunked down yet? We got all that. And this is all not that. I mean, I guess that should be an F. Okay. So that is gonna want to be somewhere close to the front. So PoE minus plus. Oh yeah, the minus is the not switched yet. Right. So yeah, we have a switch in this controller which also does the PoE initialization stuff. Right. So you're supposed to be completely off until the voltage rises above some certain voltage, and then you turn everything on. So you don't draw power at other voltages, because otherwise you're going to mess up the initialization sequence. And so this 100 nano is on the world side of that switch. Right? So this is probably going to just go. I mean, this we could theoretically put this like here, because it's kind of part of that. If that makes any sense. It's definitely on that side, right? So plunk that dude down there. Being close to this is probably not going to be a problem because it's going to be affecting both sides the same way. If we have transients on that thing. So what else do we have? I mean, these strapping resistors, sure, that's Yeah, that doesn't really matter how far they are. What's critical is going to be these. This part needs to be critical, or is going to be critical. We don't want those wires going like all over the place. Because yeah, sorry, what this is, here we're driving power, and here we're actually checking what the when the top one goes off, what is the magnetic flux in the system, and that's going to correlate with the voltage on the outside here, and so that's how the thing regulates itself, right? You see, we don't have like a feedback. Some isolated regulators are going to have like an optocoupler or something feeding back voltage information to the other side. But here we do this through the second winding, and I think there's actually a successor to this chip, which does everything with one winding. But since that's so new and uncommon, it's hard to find transformers that work together with it. So yeah, that's why I'm not using it yet. Eventually, I mean, that is the way. If you look at like the more common PoE hats for like a Raspberry Pi, they're going to be the successor to this chip, and then one of those single wound um, flyback transformers. And that's probably the cheapest you can get, which is probably why they're doing it, right? Because winding cable costs a bit of money. It's probably cheaper to do a few more transistors inside the chip than actual winding cable and whatnot, right? So, after rambling, we can return to our regular scheduled programming. This is how we can set the outside voltage. Is this divider, right? So we don't want that to be in some super noisy spot because otherwise we might be taking some of the noise. Okay, so do I want to go to that ground power or that ground power? I think I definitely want to go to whatever is connected to that, but that could also just be the other one. So lim is also a resistor. So why don't I do something like this, and then I think lim is also going to ground power. I mean, it's basically through that resistor we can decide how when the how much current is flowing through the MOSFET before it switches off, right? So if it switches on, then there's going to be magnetic resistance in the transformer, which means there's only going to be a certain amount of power flowing, and it's going to go up and up and up and up as we turn energy from the change in current into magnetic flux, and at some point it's going to turn off again as to not fry itself or the world or whatever. So depending on how much power you want to be pushing through this, you can cut that down, and it'll help you with your EMI because there's less total power flowing and whatnot. These are 0603, right? So I think I can actually get between them. Yeah, I can. And that's not going to be noisy because that's just actually, it could potentially be a little noisy. I think I don't really care because they wouldn't put it right next to here if it was noisy, like as a chip layout, from a chip layout perspective. Okay, so if we do that, and then ground power here is just for the sensing, and so it doesn't need to be thick. I could make it thick, but it doesn't need to be thick. Yeah, that's going to be pretty EMI resistant there. That voltage divider, so we're good on that. What else do we have here? What's this? Okay, that's just a decoupling cap. Well, we could put that decoupling cap close there. I think there is a way to like get power through the auxiliary winding that makes it more efficient if we do that or something. But I don't care about efficiency, at least that much in this design. I mean, we need to use some low amount of power for the switch on the other side not to think are unplugged or anything. And so yeah, I think there's like half a watt you have to take regardless. So yeah, I'm not worried. So what else we got here? What are all these guys? 10 nano. Okay, that's that side. What's this? Okay, that is this side. So it's PoE, but I don't really have anything else going on. And this is kind of a nice sort of hard cutoff as far as depth. Okay, what is this guy? Oh, that 2.49K, I already recognize that. That's the resistor class for the PoE device. So, I think I can. Wait a minute, this is bigger than those. This must be a 603, and those are a 402? Yeah, those are a 402. So why is this bigger? I guess it doesn't really matter in this spot. Okay, what else do I have? 22 micro, those are on this side of everything. That guy is also on this side of everything. That big capacitor that I'm going to change anyway is on that side of everything. The diode is on that side of everything. And this is going between. Oh, So, do I scooch stuff such that that can go on this side of things? Or what do I do? Let's see how this fits. And maybe I need to scooch stuff. That's actually okay, I think. Yeah, I think that's fine. So is there any way we could make it smaller? I guess I actually could make it a little bit, but is it really worth it? Like I could put this guy over here and then compress it. Well, no, that actually wouldn't buy me much. Oh, I guess, yeah, I could put this guy up here, move that guy, move these two up, put this over on the side. Yeah, I think I can actually do that. Just because I think we're going to be so space constrained on this board at the end of the day. Okay, do something like that, and then move, oops, that's not what I was trying to grab. Move these guys up as far as they go. Move this guy over. So we're PoE plus, and then that line, well, I guess we want to rotate it so that we're at that line. And then this guy, sorry, it's PoE minus, it's that one. Okay. And then I guess there's no reason for those not to go closer to the chip. Oops. And I can grab all of this, and hopefully nothing else. Move it down. I guess maybe I'm a little worried about spark gap when it's not initialized, although so we've got ground power to these pins, like that's already, like anything more than that is going to be fine, right? Or at least whether it's going to be fine or not is another question. It's not going to bias anything more, right? So I guess, yeah, let's just go quite close here. And then there's not really anything we can do here, but I don't care. I'm not really sure how else to do this better. I guess I could rotate it, but nah, it's good. It's fine. I guess I could compress all of these up there and give myself like a wider space here. But I could also do that in the other direction and have wider space from my controller. I think I can do it that way around. Something like that. Sorry, I want D and not G. Yeah, something like that. Let's plunk down a via here. And then we can just delete that segment and then we're good. Okay, so we want this to come down like that-ish. And then this guy here or so. Do that later. And we want this to go like that-ish. Oh, we already do all these VS, that I'm just going to delete now. That's why we don't do premature optimization, as we theoretically shouldn't. Down something like that. Yeah, then I got all this room up here for the microcontroller. Well, I guess I'm going to have to do voltage somewhere as well. Do I do like voltage here and there? So if I try and do voltage like here, then that's a question of vias being a spark gap. Oh, I could go like down from here and down from here and down from here. I think that's where I'm going to do the voltage part. Okay, let's do voltage. Yeah, the big... Oh, I'm having grid issues again. What's this crap? I'm just going to reroute everything. I hate grid issues. They have something to do with upgrading an old design to new keycad, it seems. And I think there's a workaround. I'm just too out of touch to know what it is. Not workaround, like some way to fix it more intelligently. If somebody knows that, drop it in the chat. Like there is some KiCad shortcut that just solves that. Like moves everything to some predefined grid. Oh, okay, well, let's do it this way. There we go. Okay. Oh, and I do want to connect to that. Oops. I'll do it manually. There we go. There. Okay. So the high ohm resistor is going to have the bigger voltage drop across it, and the low capacitance capacitor, like the smaller one, is going to have the bigger voltage drop across it. So it's the right way around now. And I think it updates. Yeah, it updates, right? Okay. So what I want is that to be selected in the board. And let's see how this... Oh, okay, yeah, these are big because they're gonna have the big voltage drop across them. Wait a minute. This is 1 nano though. Oh, because I haven't updated yet. But that means that actually this 1 nano can have a smaller package and this 10 pico has to have the big package, because that's where the big voltage drop is going to be. And so we need to mind the spark gap. So that's a 1206. And that one was a 603, so we can make the other one a 603. Yeah, spark gaps are something that can seriously bite you. Uh, okay, I think we got it right now. That the big distances are on the part that's going to have the big voltage drop. Okay, so up top is the mains line. Let's just build this up here. And then here in the bottom is the thing we're going to be measuring across, the like 1/100th of the up top part. Why are those snapping different? I really don't get this. Oh, that'll do. Bottle do. Okay, so this is the common. That's going to be connected to all the other ones. Oh, here I'm connecting to the lower portion. If I want to do it coming off of there, then I need to be connecting to the upper portion. And at the end of the day, it doesn't really matter. It's just which side of the Hall effect do we want to be on. It's going to be a little ugly in the schematic if we start to do that differently, but it has a reason. Are we connecting to this side? Oh, again, grid issues. Oh my god. Funny how I have grid issues on that one. There. I guess I should be consistent. Do these ones too. G is the key I'm using to do that. G is drag and schematic. Drag and pull the wires with you, right? Okay, let's update again, because I'm going to be on the right side here. Okay, yeah, so this is, I think, going to work somewhat-ish the way I want it to. I wanted to have resistor on the right-hand side, just so that it looks symmetrical. And on the bottom I had, again, resistor on the right-hand side. Oh yeah, there's the resistor, sorry, I was blind. Okay. Okay, I got that one tighter. Where did I get that one tighter than this one? Oops. I want the pad. Okay, but now it's not symmetrical anymore. What the hell, keycad? I give up. Make the grid smaller. Okay, here again, on the left-hand side, we got the capacitor. Right-hand side, we got the resistor. capacitor. Got the resistor. Okay. So that's going to be, oop, why are the labels all the way off in the middle somewhere else? Just put them in the general vicinity. I'll correct the silk screens later. Okay, so I guess there is a bit of a distance thing between these guys. I am going to have to actually make this go wider because I'm worried about the spark gap, because this is obviously wider than just one of those. So am I going to do it stuttered? I guess I have room to do it stuttered. So like that. Or something. Because if I put it right up there, then I'm not going to be within my 3 millimeters of, so what's that to that? It's also not yet quite 3 millimeters. So I need to go like there or so. I mean, it's, yeah, this is sort of just a testament to how far the sparks can go, right? I guess I could also make this more compact. Something like this. Oh, I guess maybe line this with that wall. That courtyard edge. Okay, are we far enough apart here? Oh, the measuring tool. Are we 3 here? Yeah, we're a little more than 3 here. So that's fine. That's fine. And then I'm going to do 3 down to here so I can move that up a little. I guess probably more optimization than I actually need because, yeah, okay, that's... I am going to have to worry about doing like vias close to here because depending on whether you actually have silk screen on the vias, that's going to be board dependent. And we don't need thick wires here or anything because we're not carrying a lot of current here. And then this is not a problem because there's resist on top of here, right? Or not resist, solder mask on top of here. Or Blutstoppelak, what is that? Whatever that insulating varnish is that's on the board, the green stuff. When I was thinking about like when to do the streams, thinking, well, you know, in the evening after my kids are in bed, it'll be a good time, but it's also the time when I'm tired, which is why I seem like such an idiot so often here. It's the end of my day. Am I going to do that the same just to make it all look the same? Yeah, I think I am. Oh, wait. Am I doing this the wrong way around? I guess I don't care. It'll be fine. Something like that. So that's going to be, the star point, if you will. That is going, yeah, that is going to other stuff. So that's fine. And then, yeah, so that's where I'm doing voltage. That's where I'm doing current. Current stuff can go up here on other layers. Although I guess it does have to reach that side of that because I want to do these in all the layers except for maybe the top, right? So at least 3 of the layers. But that's fine. Yeah, I think that'll be good. So what do I still have? Still have, oh, this is going to be tight. I might have to start making more stuff smaller because I am going to have to, like from this point, this is the point that's, I guess I could draw on fab, user drawings. It's called user drawings. Let's go from like that point. A 3mm. Oh wait, I'm at 1.8 here. Is that actually enough of a spark gap, or do I need to use bigger components? I might need to use bigger components. Because that might not be enough. Although I guess it's wire to theoretical star points. That's going to be half the voltage. And it's a little more than half the distance. Although whether it is actually half the voltage in all cases. Did I mention main stuff is hard? I think I'm going to keep thinking about that. Like in the fault scenarios, whether the star point is basically in 3-phase power. It's the the theoretical 0 volts, right? So average between all 3 is always going to be 0 because some are going to be negative. There'll be 2 negative and 1 positive, or 2 positive and 1 negative, or 1 positive, 1 negative, 1 in the middle. At any given time, and so the average of all 3 is always going to be like the center point. And so like the theoretical maximum voltage that I'm going to see is going to be from point to point is going to be almost twice as much as to the star point. It's not going to be quite twice as much because you don't have like the lower side at its highest point when you have the higher side at the highest point. It's going to be, when the two lower, if you will, two lower are both at the same level, and the top one's at its highest point. And that's theoretical maximum voltage you're going to see. And so, yeah, it's not quite half to the star point, the middle. So that actually almost kind of works out if it's not quite half, and 3 is what I'm using there, and that's 1.775. It'll probably be okay. I'm gonna note that and think about that more before I actually order the board. I might leave a comment with the result of what I thought about. Okay, so 1.775 from this point on is the arc that I want to draw, so that I know where other components should be at one point. Yeah, or here-ish, right? So yeah, so I want everyone to stay out of that. That's the whole point of doing that, right? So microcontroller. Oh, I got the thermal wheels on the. This theoretically shouldn't be happening. Why is this happening? Oh, because I used to. Let's change the footprint. I guess I want to change the footprint on the other side. So this footprint should actually be QFN 56 with a 7x7 pad was, I think, the, it's not a custom footprint. I did at one point, and then I realized that KiCad actually has it. So I should be using the KiCad one without the thermopias. Package, QF, and DF and QFN. That's why I wasn't finding it. Okay, and then we're a 56. No? Oh no, we're not DFN, we're a QFN. With 56, 7x7. Or no, sorry. Yeah, 7x7 and then exposed pad. I think this is the one. Or is this the one? Or is this the one? That's not the one. It's not that big. I'm just going to go with that and note that I should check it. So you guys have to wait for me to check it. But anyway, so this is more like it. And then all of these guys are 603 or what are they? Yeah. So I probably want to change them to smaller because I have to fit the whole network PHY chip in between here. And I can't make some of these I can't make smaller because they actually have stuff going through them. Why don't I just scooch all this up, move all this out of the way. What is that? Oh, that's the ADC. Oh, I've got all that stuff to plunk down too. Although that will probably go over there. So why don't I do the same thing here that I did there. Just to show, and then do like ADC stuff here. Okay, so why don't I check the ADC sheet? Where are we? There we are. I actually should figure out the RP 2040 has like a clock output thing because we've got like a crystal here and we got a crystal down here, and the RP 2040 has its own crystal too, which is 12 megahertz, and this one's 25. So that actually might not be all that easy to make a 25 out of the 12, but I guess depending on, there are PLLs in there, but jitter and whatever. But this crystal shouldn't be, we shouldn't need this crystal really. If we were penny pinching, I'd do that in firmware and set it all up and blah blah. But yeah, that component's not going to actually make it, be the deciding factor. We're not going to be selling tens of thousands of these things. We may, like there certainly are use cases for tens of thousands, but we don't have that kind of sales department. Okay, so what are all these guys? Okay, well that's that. There's too many of them for it all to be that kind of stuff. Wow, that's a decoupling cap. Fire bead. Okay, this is, yeah, I guess that's all legit. So here, ADC, here, RP2040, and here. That might actually fit. That's kind of cool. So why don't we have a look at this sheet and start with magnetic side of things. So these are the ones going to the magnetics. And so I guess this. Why don't I select all of those just so that I know that that's what we're dealing with. So that is what's going to be going here at the bottom. Oh no, I have to do the power stuff first. Ew. Okay, so that guy, this side of things. So I'm not going to be able to make these smaller, I don't think. These are probably the right size as well. Okay, so what size are those capacitors? Boop, boop, boop. 805, do they need to be 805 or can they be 603? 20 UF. Sorry, I gotta check the JLC. I guess I can pull it in so you guys can watch me do it. Okay, what do we want? All components, ceramics. We want micro, what was it, 22? Let's see what we got in basic. Well, that starts in a 603. I don't think we have to be too worried about derating on a sucks that they don't do derating like in the data sheet. It's usually on the website. But if you search like this, then usually you can find it. Samsung Electromechanics should be down. What? Yeah, okay, it just took a while to load. I was worried. So at 5 volts, oh, we do have some serious derating. 5 volts, we're down 68%. What about the 805? Oops. No. Okay, the 805 is this guy. This guy, let's see. I wonder if we can just do this. No. Oh well. Samsung mechanics. Let's check the derating. Oh, that's not so good either. What, we're at 5 volts. Oops. Well, 51.5 is not as bad as 80. Yeah, I think we're going to leave that 805. And then we did want like a giant one. Reset all. Min, what do we want? 100. Basic. Let's see if anything pops up. Okay, so there's one. 100 UF 1206. Let's see what the derating on that sucker is. That should be pretty devastating, I'm assuming. Oops. Yeah, that's the one we want. Okay, no, that's actually, oh yeah, well, because it's a 6.3 volt, moves the whole thing. So we're at 70% derating. Foo, 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 foo. Do we go with a 47 in the same 47 basic? Oh, there we go. So that's a 10 volts. So that one I said was 70. This is half the nominal, but at 5 volts, it's, oh, that's actually not that much better. Guess I should be just going with the 100. What did I say the 805/22 was? Where's there 1206/22 with a good derating? Why don't I look at both of those? Now, this is taking up a lot of time, but this is actually, if you're space constrained, like one of the things you probably want to fiddle around with, which is why I'm doing it on stream, because it's actually something I fiddle around with. You know, how do you pack the most power into the right size? Okay, so oh yeah, okay, we are here at 5 volts. We're down 40 on 1206, and then on the 805. Oops. Down 50, but it's more smaller. So why don't we go with the 805/22, and we want like nominally or actually 100 or something. Or do we need 10 of those? That's a lot. I can see why I was thinking about using that big beefer here. But do I want to use that thing? Did I actually check what LCSC number? No. Do I want to use a tantalum or aluminum electric or something like that? Cost, not really a problem, like 1.4 cents in volume, that's nothing. It's more of a board space question. And in that space, where I have like a 805 for reference, in that space, I can do like 1, 2, 3, 4, 5, 6. Like it's not actually saving me all that much space. Maybe I should just do 10 of the small ones. I mean, you do have to worry about like the ultra low equivalent series resistance you're going to have if you do a bunch of ceramics in parallel like that. with buck regulators that rely on seeing some ripple, because you're just going to kill all the ripple, if you will. Uh, so yeah, that's something to think about if you're doing this kind of like a bunch of smaller ceramics rather than one big electrolytic. But in this case, with the flyback, it doesn't need the ripple, so we can just go crazy. It'll actually lower our electromagnetic output, whatever that's called. It'll help us pass EMC. Okay, 1, 2, 3, 4. Maybe 8 is enough. Like, we're not going to be using that much power. And we can actually tolerate some ripple. Thinking about this further, we can actually tolerate some ripple over there because we're going through an LDO afterwards. Now, the reason why we're going down to 5 and then through an LDO, like there are coilcraft transformers that have a 3.3 output, but they actually have an inductance which is out of spec of this chip. Like this is not a pair that is like made for each other. It just works out with the 5-volt and up versions that it does work with this chip. Whereas the 3.3, like you can probably tweak it to kind of get it to work. Like I have gotten them working, but it's finicky and I don't want to have to trust it. So yeah, that's why I am going from PoE down to 5 and then from 5 down to 3.3 with an LDO, because that also allows us to tolerate more ripple here. So this, I think, is going to be fine at this point. It's enough storage for stuff coming out of here to survive until the next pulse, right? I mean, that's basically all that matters. So here we have our nice bunch of beefy, what's the connection there? Okay. Bunch of these dudes. Now, what? This thing is glitching. Oh. I have no idea how I keep changing that grid. I think it might be like mouse wheel and some key or something that I keep hitting, or whatever the deal is. Okay, I guess that's one of those. And then that's also one of those. So these are the things that are not like the others. Okay. So I can do the same trick and start down here. Actually start a ways down here. I mean, we do have to worry about this spark gap, right? But this is going to be the actual deciding spark gap. What are we aligning with that for? God, what the hell? How do I turn that off? Anyway, so yeah, so it's going to be 2.8-ish, which, as we saw up here, is if you're super safety whatever, then that's actually probably not enough to get to the nominal 2 kilovolts. On the other side, we're not going to actually see 2 kilovolts, so it's fine. Yeah, if we were like doing medical devices or something where you really, really have to be 2 kilovolts, then yeah, we probably would want to make sure that that is all correct and whatnot. But in our use case, it doesn't matter. Okay, do I want to just kind of keep shoving these down this direction? I think I do. see if I going across like this. Oh, wait. That's actually kind of not logical, what I'm doing there. I should be going something like this, and then scooch around the outside with that guy, and then I've got 5 volts up top, and we go across like this with the ground, and we'll eventually get there at ground, and it'll just be a nice big rail. I guess I could check the stream for comments. People somehow haven't been giving as many comments recently. I had one stream where there was a bunch, and I thought it was pretty cool. But I don't mind them being YouTube questions either. Or, you know, you can hit me up on X. Okay. So this is the tame side of that, so we don't have to worry about getting close to that. We just keep on going. Keeps on going and going and going. I guess I'm dating myself. People remembering those Energizer Bunny commercials. Something like that. Okay. Then now we can go from there. I could probably smack the LDO in here somewhere, and then there, I can scooch that one down and smack the LDO in there. And so now we're interested in these guys. Although I guess I don't really care about matching them up to something there, so I guess I care more about matching them up to the chip. So why don't I figure out what side of the chip those are all going to. Okay, so it's like that corner. Okay, so there's one diff pair, there's the other diff pair. So why don't we match to the chip. Now, we probably are going to need one wide cap on that side. And so that wall is going to be decided by that. So why don't I get one decoupling cap. So that should be a decoupling cap. 100 nano, VDD to ground, just so I have like a reference width. Okay, so that's how far the wall is going to be away. And then we can just start with this. So we could go that direction, or we could say we're going down. Or we could go down, down, and see what that's connected to. Maybe do like a... Oh, okay, so that's going to VDD. So we could start with this. And then do like this. And then do the TXP here. And then TXP coming down like that. Or do I do it like that? Or do I do it even more compact? Like, do I do... this like here? Guess I need another decoupling cap in between there. So I won't have the room really. So Yeah, I guess I could go the other way around here, around there. I guess I could have done both of those at the same time. And then start like way up here. Because then I can go like this, and this, and this, and this, and everything's great. And there, okay, I'm going all the way there. So let's look at these guys. These guys is where I think I also have a capacitor in between. But although I guess maybe I should plunk down the what capacitors on pin 4. Pin 4. I guess I could just grab one of these and use that for pin 4's decoupling cap. Okay, and then after that, that's when the resistors come into play. Now we're be able to get around that, and then maybe we need a little more room. Also allow us to scooch that a little higher, but that is, I don't care about that yet. Okay, and then we got pin 8. That's just, let me grab another one of those. Is that one available? No, that's the one I already used. So how about this one? Just want to decouple that. VDD. And then what we got here? Well, that could be long. Like, there's nothing bad about making that one long. Wonder pin 11 and 8, if we wanted to couple those both to the same capacitor. Maybe we do want to make this, like, scoot just over. Not do this, because we're kind of running out of room over there on the right. Go something like this. Because then that's going to be connected to that. And then we could do X press right here. And then for that VDD, we need to just grab another of these. Okay, and then we've got stuff going on here. And here. Okay, so if we did that, just kind of start there, and then, because I don't really care where these go, because it's going to be, you know, coming from underneath up to that point. coming from the second layer, and so we can just smack these guys on here. This is going to be a terrible silk screen thing, but I don't care about that yet. And then we need, then we need these guys on that side. So am I going to do this one first? No, I'm going to do the other one first, and then that one's going to just kind of scooch through below, because I can go through the middle of that one. It's going to make that line all along. That's going to make it a little noisy, but I don't know that I really care. It's going to work. Well, I guess I could actually do, no, I could do this differently. I could do it like this. Because then everything's nice and small. Okay, I think I'm quite sure that this is the right way to do all of that. It's about as compact as I can get it. Now if we plunk this down along this wall, silk screen's just going to be terrible. Oh well. You don't need silk screen anyway. Maybe I'll just make it tiny. Okay, so now we have the rest of this stuff. Just part of that. Oh, we're going to fit. I'm pretty sure we're going to fit. Now, AEC will be a little tight, but yeah, so why don't we do this side just one wide of just get this all rooted up so we see kind of visually how things are going to work. We're going to be a 2-ounce board anyway, so I don't really have to worry about track widths on this kind of stuff, right? Board's going to be thick. Okay. Another thing you have to worry about with thicker boards is if you have, am I drawing? Yeah, I'm drawing. Oh wait, yeah, no, I'll just use this to erase everything. So if you have like a, oops, your board surface and you've got copper on top going like this for like that width. Well, that same width of track with a thicker copper is going to be, something like that or even higher, right? That's not going to work, right? So as your board gets thicker, the min track width that's going to actually work is going to be have to get wider, right? But I think we're within that tolerance with our 0.2 mil track width. That's fine. That'll work with a with a 2-ounce board. Yeah, that'll be fine. Okay. Am I going to do super thick? I think I'm going to do super thick just for the fun of it. Okay, so the main amount of power is going to be flowing through like that. Well, that's pretty ergonomic. And that can do skinny one here, because that's just for swallowing the flyback. Like if that, yeah, it's not going to get all that warm. Okay. So, what was I doing here? So I guess I just have 2 decouplers left. Why do I just have 2? I think I need more. Oh, that's even a resistor. I am kind of at a loss for why I don't have more of these. So why don't I do 2 things? Why don't I... Oops, using X because that's the wire in the schematic. Here it's W. So why don't I make more of these? But also, I think I could do like group edits. I think that was a KeyCat update a couple years ago. So I think I can go through like all of these. Right, E, nothing's happening. So I guess I can't edit properties of all of them at the same time. Well then. Oh wait, I do have properties up here. So can I do value? I can't do footprint all at the same time. Because I kind of want to do all of them in 402. It's probably taking way longer than it should. Do I have any 100 nanos that are not part of the low voltage part? They should also not have a DEG part number. I don't do that anymore. Just do the LCSE. That means that part number is going to be wrong too. I'll fix that later. We got the size as well. Note that down. Okay, now they all got smaller, which is kind of cool. Which means we could theoretically move the whole thing left a little. Do we really care? Actually, we might care, because over here we got the ADC. Yeah, let's scooch it. So we actually have that VDD. I wonder if we could scooch it like all the way, like move this down to where it's not there. I mean, we don't want to get too close to the edge of the board actually with the components. Yeah, I think I'm just going to move and then reroute. Because that way we got way more room over here. And this side I think is like a lot of like alternative, like external PHY stuff that I don't care about anyway. That's why there's so many dang ground pins, because they're all just kind of grounded out. Input lines and whatnot. And the no connect would be the output lines. Yeah, okay, so I think if I hovering over a track and hitting U will select the whole track. That's another common shortcut you need to know. Okay, well, I can also contact things because that dude's smaller. Why don't I also do that? It's going to mess up a whole lot more with my routing, but I don't care. I need the space. Okay, well, that's already screwed up anyway, so let's just keep moving these. Okay, here I think I can drag with G, and it'll all work out without creating any DRC errors. Dragging with G, dragging with my G. Anyway, there's a German saying: after fatigue comes stupidity, and it's quite fitting. I always do the stupidest things when I'm tired, and I'm a bit tired now. My smallest son fell out of bed yesterday, so that was quite the less sleepy ordeal. And my wife was worried about him, which is, logical, and it's what wives are for. She didn't sleep. He didn't sleep. I didn't. Yeah. Okay. Not that I want to discourage anyone from having kids. Okay, if I can't get around, I guess I don't really care. I'm going to plunk a via down here anyway. And this chip is, well, I guess it's nominally 125 megahertz. That's actually quite a bit. Maybe I do care. Oh, cool world. Does G work with multiple components? No, it doesn't. Okay, one, multiple. Well, I guess I wanted to get to that ground. I think I'm going to turn that one around. Oh, but now I'm running into the same problems there. I do the G here. Oh. Yeah, I mean, the power integrity on the network stuff is actually some of the more important part of doing all of this, so I really probably should try and get this right. Which means scooching everything a bit so that I have room, even though I just scooched in the other direction. D rather than G. Okay. I guess how would you formulate in human words the difference between D and G in that case? Ah, Leute. I mean, the courtyards are a little too big on those guys anyway. Let's just do this, and it'll be fine. Okay. Do I have any major DRC violations going on? No, just those two resistors are closer than the courtyards would. But yeah, no, any pick-and-place machine worth its salt will still be able to do that. So, we're all good. We're all good. So we wanted to, yes, we wanted to do the decoupling of those. And we're going to do it like so. And we're going to do another one right above it because there's another pin. Or was this the side with the phi stuff? I don't remember. Okay, X cap. That's 4.7U. Does that need to be smaller? I think so. Make that a 402 as well. Probably should be some serious derating on the 402 4.7U. Do we want to check that out? Oh, I'm going long. I'm already going long. I'm in my element. So I guess, yeah, why don't we stop here? Because I'm already 15 minutes over. In the zone. Yeah, so thanks everybody for watching. I think we're going to take a whole nother episode to do the rest of this. And by then, I will have thought about the things that I wanted to think about. And it looked, I'm pretty optimistic that we're going to be able to make it fit. And so, yeah, next Saturday, aspirationally, we're going to do the rest of this board. And if you have any questions about any of the stuff I'm doing, then feel free to hit me up, and I will ask to answer them either directly or in the next stream, or probably both. And take care, everybody. And I hope you have a nice rest of Saturday or Sunday, middle of the night, depending where you are in the world. Take care.